Hey guys, welcome to the next Diels Alder video. So this time we're going to be covering intramolecular Diels Alder, alright? So again, it's going to be a lot of the same stuff you guys already know, so it's not going to be that bad, alright? I know a lot of people don't like intramolecular reactions, but we're going to try to hopefully simplify it down, okay? So we're going to use this example problem to help us, and so it gave us a structure and they asked, give us what's the product of the Diels Alder reaction, okay? So let's look at what we have. So in the intramolecular Diels-Alder reaction, we're going to have a diene and dienophile on our compound, right? On one compound. So what first thing you want to do is figure out what's your diene and dienophile. Here's that diene. Here's that dienophile, that one double bond. Okay? So now that we have our diene and dienophile, we can get started, and I'm going to redraw our compound here. Okay? Alright. So remember, in a Diels-Alder, you need the S-cis conformation, right? If you look at this diene, it's in the S-trans. So first step, rotate that and put it back in the correct position. So all I'm going to do is divide it in half. And I'm going to just flip one end just because it's easier. I'm going to flip this end. So it's going to look like this. So here's our diene. All right, it's in the S-cis conformation. Now we can get started with the actual reaction. So remember, what you want to do is you want to always number first. All right, so I'm going to number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we got 10 carbons here. So let's see. Remember that we're going to have to connect the diene and dienophile. We're going to connect these carbons to these carbons. Now, because this is intramolecular, it's actually a lot easier in terms of the regiochemistry. The reason is because we can't create any weirdly formed rings. So my strategy was I looked at, let me actually just clean these numbers up. All I did is I connected the closest two carbons and the furthest two carbons, and you'll see why in a second. So this is going to be carbon 4, 6, 8, and this is 10. So I'm going to connect 4 to 9, 1 to 10. All right. So now, the reason I did this is because this always helped me see the rings we're going to form, because you're going to form a ring from your regular Diels-Alder, but the problem is because there's a chain here connecting the diene and dienophile, we're going to have two rings, and you could probably have figured that out just because of the answer choices here, right? And so here's the reason I did this is because if you look at it now, one of your rings is right here. 1, 2, 3, 4, 5, and 6. The other ring, I'll do that in purple, is going to be on the interior. 1, 2, 3, 4, 5, 6. So you see they share a side. Okay? So that's the reason I did this, because it just helps me a lot easier figure out the product. So now what I'm going to do is I'm going to draw that 6-member ring we always know forms. Let me make that bigger. Alright? And so let's number the carbons of our ring. Now be careful here. The way I numbered it, I'm going to number, let's say, 1, 2, 3, 4. But now the other two carbons in our Diels-Alder ring are 9 and 10. Alright? So just be careful about that. And make sure you keep it consistent. 4 is connected to carbon 9. 9 is connected to carbon 10. And 1 is connected to carbon 10. Alright? So now we have one of our rings, but remember, keep in mind we have this interior ring too. Now to figure out how to draw this, let's just look at this. You have carbon 4 is connected to carbon 9. This bond right here connects them, and it's shared with that other ring. So we know that the other ring is going to border 4 and 9. All right. Carbon 4 is connected to carbon 5. So let me just move this over. Carbon 4 is connected to carbon 5. 5 is connected to carbon 6. 6 is connected to carbon 7. 7 is connected to carbon 8. And 8 is connected to carbon 9. Alright? So the key thing to recognize is that these bonds that I drew, this like green bond, is connected to 4 and 9. And that 4-9 bond is also shared with the other ring. So that is the reason we put the other ring connected to carbon 4 and 9. Alright? So now we have that, and what I'm going to do is, if you look at the answer choices, the rings are side to side, so what I'm going to do is I'm going to just rotate this. Alright? You didn't have to rotate it. You could easily do these problems without rotating anything, but it's just sometimes a little bit easier. Okay? And so here's our 2 rings, right? So 2 6-member rings. As you can see, we have choice F has a 5-member ring. We can cross that out. Choice C has a 5-member ring, and choice A has a 5-member ring. Cross all those out. So you see now we've already brought it down to 3 choices. All right, so we're almost done. Now let's see. We didn't draw in our double bonds, and so if you look, carbons 2 and 3 would get a double bond. So let's put that right there. All right. Now we can eliminate already another answer choice, because if you see this double bond is 1 carbon away from that that bridgehead. All right. And so if you look, choice B has the double bond right here. That's 1, 2 away from the bridgehead. That's also wrong. Eliminate that. All right. Now D and E have the double bond correctly, so we can't eliminate anything yet. So now let's finish out the Diels Alder. All right. So what we have to do is we have to put our withdrawing group. Right. We have that CN group, and that was on carbon 10. So let's place that. Just erase this. And remember, I always like to leave things planar first and worry about the stereochemistry at the end. So now we have all of our substituents placed. We didn't have anything on the diene to worry about in terms of like any donating groups. So we have nothing there. What we now have to do is do the stereochem. Now here's the thing about stereochemistry when we're doing intramolecular Diels Alder. You learn that when we did the Diels Alder with a separate diene and dienophile, right? We had the endo and the exo product, and that the endo was the major product. Now in Diels Alder, when we're doing intramolecular, that isn't always the case. We can get endo or exo. We can't really guarantee any one of them. So when you're doing this on a short answer, you can draw the endo or the exo product, all right, and they will be counted correct. On the multiple choice, they could give you the endo or the exo as the correct answer. Now, most of the time, I've always seen it being the endo, right? But they could easily make it the exo, so just watch out for that. So that's the reason that when I did intramolecular Diels Alder for any multiple choice question, I always looked for the endo. I always made my product look endo, and if I couldn't find that, I just switched up the stereochem, looked at the exo and saw if that was there. But 99 times out of 100, it was the endo product. Okay, so let's just finish this now. So I'm going to erase these over here just to make it a little bit easier. All right. So remember, we always want to make our trans groups from the diene have the same stereochemistry as the withdrawing group. Okay, now what are our trans substituents? All right, what I'm going to do is I'm going to redraw this over here. Not the whole chain, but just enough so that we can see what's going on with the diene. All right, so if you look, our diene is right here. So what are the trans groups? Remember, the trans groups point outwards. In this case, they're going to be pointing this way, right? The cis groups are pointing inwards, so trans, cis. So because nothing was written here, we know that there's just hydrogens. A hydrogen outward, hydrogen inward, and another hydrogen inward over there. But the trans group, that is the hydrogen, let me change the color, this hydrogen and this chain, all right? So that's another important thing, all right? It trips up a lot of people. That is the trans group, the whole chain. So that 4 and 5 single bond, we can think of that as our donating group. Or not a donating, as our trans group, right? And there's also that hydrogen. So this single bond and this hydrogen will have the same stereochemistry as the withdrawing group in the endo product, obviously. Okay, so that 4-5 bond is that bond. The hydrogen I was talking about here was off of carbon 1. So that's that hydrogen. All right. Now in this case, that hydrogen off carbon 1, it's not a chiral carbon, so we don't need to worry about it. All right, so I'm going to just erase that. So what we really need to focus on is carbons 4 and 5. Okay. So let's see. What I'm going to do is I'm going to make that one, right? Let's say I'm going to make it wedged. I want to make that bond wedged. So carbons 4 and 5. So that bond to 4 and 5, we're going to make it wedged. But remember, we don't like to draw rings this way, right? We use hydrogens to represent that. And so if the bond here at 4 and 5 is wedged, the hydrogen here would be dashed, all right? And also, just in case you're wondering, that hydrogen that I just drew in is that interior cis hydrogen, which makes sense, right? This and this should have opposite stereochemistry, right? If you remember back in the one of the earlier Diels Alder videos, we had this little diagram here. Right, the trans group here is that single bond from 4 and 5. The cis group is this hydrogen. They have opposite stereochemistry, right? So that should hopefully make some sense. So what I'm going to do is I'm going to erase this little wedge because we don't need it. We use that hydrogen to represent it. All right, and so if I made that single bond between 4 and 5 wedged, it's going to want to have the same stereochemistry as the withdrawing group. So we want to make this guy wedged. All right. Now the last step, if you look in our choices, all these the hydrogen at the top also has stereochemistry. All right. So we're going to have to finish that out. And so what we're going to do is you're going to look at because that hydrogen is on the carbons that were part of the dienophile, 9 and 10. All right, let's just look at that. I'm going to erase the green lines over here. So off of 10, we have a hydrogen also. Off of 9, we have this hydrogen. All right. And so if you look, this group right here, this CN group, is trans to the rest of the chain, right? Back to orgo 1. So that's trans. And that also means if that CN group is trans to that chain, then it's cis to this hydrogen, right? You can see that if you just draw this in half, it's on the same side of the double bond as that hydrogen, coming off carbon 9. All right, so that means it should have the same stereochemistry, which again would kind of make a little bit of sense, right? If the CN and the hydrogen and that CN group have the same stereochem, then this single bond right here between 8 and 9, since it's trans to CN, should have a opposite stereochem. So that means if this is wedged, this would be dashed, that single bond between 8 and 9. Alright, but again, we don't like to represent, we don't like to draw these wedges and dashes on the rings themselves. We like to use the hydrogens to represent that, alright? But just keep in mind, they could easily show it to you with this dashes and wedges on the rings, alright? But most of the time, it uses hydrogens, alright? So I hope this video helped you guys in terms of the intramolecular Diels Alder, alright? But, and just like I said before, I drew the endo product, and the answer here is actually D. Sorry, I forgot to say that. And that is the endo product. But they could very easily ask for the show you the exo product. Multiple choice, usually it's endo. Like I said, 99 out of 100 times it's going to be endo. Short answer, it's up to you. You want to draw the endo? Draw the endo. If you want to draw exo, draw the exo. I always prefer endo just because when we did the regular intermolecular Diels Alder between two compounds, endo was always the major product. So we just always kept it consistent in my mind to draw the main product for the intramolecular as endo. Okay? And so I hope this video helped you guys. Remember, you always want to keep practicing Diels Alder. It can be tricky at first, but if you practice it, Diels Alder problems are going to be very simple for you. All right? It's very stepwise. You can kind of create yourself a little bit of a guide to help you get through all your questions, right? Because it pretty much always takes the same order. First things first is just make sure you have the cis conformation for your diene, all right? Next thing you're going to do after that is the regiochem, right? Draw everything planar. That's my trick. Draw everything planar, and then worry about stereochem, all right? Hope this video helped. I'll see you guys in the next one.